We like to see things with our own eyes and touch them with our own hands and smell the air around us to develop a sense of reality. But in the great depths of our oceans, this is impossible. In some ways, the moon is more real to us. At least we can see its major features with our own eyes. Primarily using sound waves, we have slowly and steadily been gathering information on the physiography and geology of our vast oceanic basins. The images created by these sound waves have assisted us in developing the theory of plate tectonics and help us clearly see the plate boundaries. There are countless fascinating features that have been revealed to us, and some of the most interesting to me are great river-like channels which wind their way along the ocean floor, some of which can be traced for over 2,000 miles into the great depths of our oceans. How did these form? When did they form? Are these ancient rivers that wandered across the seafloors when there were no oceans? The presence of these channels provided a wonderful puzzle for geologists to put together. Furthermore, the understanding of the processes that created these features settled the debates that geologists had about many rock outcrops around the world. Let's go see an outcrop that would have confused geologists back in the day. Hiking up this steep slope gives me an opportunity to reflect on the work I did for 2 summers on these formations 11 years ago, and how exciting it was to find the outcrop I'm hiking to. I also think about the world about 100 million years ago when a great seaway formed within North America named the Cretaceous Interior Seaway. It was within this ocean that these 2 great layers of shale were deposited over a period of about 4 million years. The lower darker colored layer is composed primarily of clay shale and is dark colored because it has organic material within it. The upper lighter colored formation is also a shale, but it formed primarily by the deposition of microscopic plankton called radiolarians. They have shells made of silica. Based on the fossils found in both units, they were clearly deposited in the deep open waters of an ocean. I still have some climbing to do to get to my final destination. It's this tiny little spot. I'm finally getting close to this amazing outcrop. It's a fascinating one, very confusing back in the day. I've just got to scramble across this steep hillside. Fortunately, it's quite soft, no real danger to me, but I'm getting there. The outcrop is as fascinating to me as it was 11 years ago. The feature is quite unusual, as it is only the second one I found in all the exploring I did. This lenticular-shaped body is composed of very fine-grained sandstone and silt. Looking carefully along the base of it, there is clear evidence of erosion. The layers of shale have been cut into. It looks very much like this typical cross-sectional view of a sand-filled river channel. What I'd like to do is imagine being say 2 or 3 geologists that had come up to this outcrop in the early 1950s and the discussion that ensued. Because I'll tell you what, this would present some challenges to them. And the geologists at the time would be looking at this and going, well, how did this get out in deep water sediments? There'd be at least one geologist that would immediately say, I know how. We just lower sea level a lot. And I do mean a lot. We'd have to lower it way, way down, 1,000 feet or so. And then we expose all that mud out in the ocean floor that was deposited prior when the sea level drops, and the rivers would come out across all that mud, and they'd cut channels like this relatively small channel here. And they'd cut into there and leave a river deposit just like the rivers we know. And then the discussion would get interesting, because another geologist would look at this and say, so you think that's a river deposit? And that the sea level dropped dramatically. You know what would happen if we dropped the sea level dramatically? We would, right on this contact, right here, where this channel cut into, all along this contact, we would see erosion all over along it. Because it's soft mud, the sea levels dropped, and it would just, it'd just be in a very interesting surface to do that. There wouldn't be just this one channel. There would be tiny little cuts and erosion all through it. And you could trace it along this outcrop, and all around you could find it easily. We call that an unconformity. And that geologist would say, you know, we've been hiking all around here, and in fact, we're going to hike around the corner and look, but I haven't seen anything like this. This seems to be alone, standing alone right in the middle of all this ocean mud. Furthermore, he would say, you know, when you drop the sea level and you expose all that nice mud out there and it dries out and the rivers come across and cut channels like that, if you're going to say that occurred, where's all the vegetation, all the root casts, or evidence of roots from trees and grasses? And where's the soil that developed? So not only don't we have the erosion, we don't have any evidence of this sea level dropping, where you would develop the soils and things like that, and vegetation. So, boy, that'd be fun. You know, they wouldn't know what to do. They would toss it back and forth, and they would scratch their heads and wouldn't know what to do. They'd finally probably decide that, well, this is just a very highly unusual unconformity, where it only eroded this one place, and for some weird reason we don't understand, no soil had developed or no evidence of vegetation right here. And they'd just have to leave it there. But you know, by the mid-1950s and beyond, there was a lot of information that was starting to come in from work being done on the deep ocean floors, especially off the coast of California. And people were starting to understand, scientists were starting to understand that there were some really fascinating processes that were occurring out in the deep water. And with this information, this took quite a period. And in fact, it continued for many years, decades, getting more and more information as to the complexities of the processes that are occurring, did occur, and are occurring out in the deep water. And with that information, now this outcrop isn't so puzzling at all.
Geologists had steadily accumulated data, albeit very sparse, on our ocean's floors for decades leading up to the 1950s, and had developed geologic models to explain the observations. Let's follow in their footsteps using modern data. This wonderful map that we'll be using is compiled by the United States Geological Survey and is an elevation map. The violet-blue color is the deepest water at 15,000 feet plus. An important feature to our geologic journey that had been known about for 100 years or more is the continental shelf. It is composed of sediment that built out over the last 5 million years or so. Most of the shelf was land during the ice ages, when sea level was about 300 feet lower due to storage of water in the vast continental glaciers. In the late 1940s and early 50s, scientists noticed something significant in this area off the coast of Washington state. At a very regional level, what do you notice out beyond the continental shelf? What two basic types of topography do you observe? Same question for the Arabian Sea region. What I want to focus on is the smooth versus rugged topography. Why do you think there are these two surface types? Looking along the west coast of Africa, one has to wonder if the rugged surface with all the fractures actually continues to the east underneath the smooth surface. Geologists pondered that very question and decided that it does, and that the smooth surface is the top of sediment that had slowly accumulated out in the deep ocean hundreds of miles from the coast.
To my trusty whiteboard. I've got my tree here, so we know we're looking sideways, a cross-sectional view. This is the ocean here. The continental shelf would be right here, and we have sediment with these dark lines filling in. The seafloor, the original seafloor, is in red, and the sediment is covering over much of it until you get further out, and then it gets more and more rough because there's not enough sediment covering this rough red seafloor. The world, according to geologists before the 1950s, was that most of the deposition out here near the shoreline was delta deposits and beach deposits and things like that, much like it is today, and that is building up very quickly here because the sediments in the rivers would quickly drop out near shore. Now there's muddy water that you've seen that makes it out further into the ocean, clay-sized particles floating in the ocean column, and it can go way out here, and it gently falls down to the ocean floor, and it's called, we refer to it as pelagic rain or pelagic deposition. Think of it as kind of like dust settling down and building up. And it would build a wedge. It would be thicker here of sediment and thin out further and further as you go because the deposition rates are lower. So it all makes sense. There are observations. You'd have a very smooth surface, the abyssal plain, because it had built up and covered this rugged surface. And as you got out further and further, you would have this rugged surface exposed and almost no deposition way out here, very low deposition. This is a nice, tidy explanation for the observations we have. But you know, new data comes in. And then Mother Nature throws curveballs at us, and this was no exception. I want to zoom in to one of these little ridges that are partially covered here and show you what happened, some of the observations they made. So I've added more drawing here. This area here is simply a close-in view of one of these, I'll call them ridges, one of these bumps that we see here. They're actually ridges, I'll say, for this discussion. And here's the sediment, the smooth surface that we've been talking about out in the abyssal plain, a pelagic sediment according to their model. And on this side, we have the top of this pelagic sediment here. And this is what they observed. And this was a problem. This doesn't fit the model. Why would I say that? Well, let's think about it. If you have pelagic rain, kind of like snow, wouldn't the thickness on both sides be the same? Wouldn't this surface that we see here just go right here and continue right here across like this? But it doesn't. How does that happen? Well, I know there's probably at least one geologist, I'm sure, that said, well, I think we've got a solution here. We can just put a fault here on this downslope side of this ridge and drop the whole seafloor down. And that means this whole surface is dropped down, and the actual pelagic sediment really is the same thickness as we'd expect on both sides. So that solves that. And that is some good thinking. Yeah, okay. Not so fast, not so fast. We observe this a lot on a lot of different ridges. So now we're in a situation where we have to say, well, on all these ridges where we see this, there happens to be a fault only on the downslope side to drop this down to give us this weird situation that we're kind of concerned about. And they made some more observations as well that gave them more concern. And they started to believe that in reality, the sediment on top of the seafloor was actually thicker on this side than this side. And geologists have to explain that.
Geologists had known for decades prior to the 1950s about these great canyons that cut across the continental shelf. But what they did learn in the 50s and puzzled over was the shape of the ocean floor out beyond the canyons. It is often fan-shaped and is displayed nicely here at the Congo fan. The perimeter of the fan is about 350 miles from the shoreline, and the water depth is about 14,000 feet. We'll return to this fascinating fan shortly. The fan offshore of the mighty Amazon River is something to behold. It's easily 700 miles across the width.
The recognition of fan-shaped surfaces at the mouth of large canyons cut into the continental shelf forced geologists to completely reconsider their model. They were very familiar with the processes that formed fan-shaped deposits, such as alluvial fans and deltas, or small fans formed by avalanches. They knew that in each case, sediments are transported along the ground by rivers, streams, or avalanches to deposit sediment in a fan shape. Some geologists thought that the sea level must have been very low in the past, much, much lower than they had previously thought, and that these fans had formed as deltas or alluvial fans out onto the former seafloor. This idea was somewhat believable because they first observed these features in about 2,000 or 3,000 feet of water. Maybe sea level dropped 3,000 feet instead of the 300 feet they had previously believed. But more data came in, and they saw that the fans continued out into water depths of 10,000 feet or more. This observation forced all geologists to accept the other prevailing theory, which was that there are underwater processes they didn't understand that transported sediment far out into the depths, building these fans. This theory also explained the sediment distribution near ridges and other obstacles that we talked about on the whiteboard. The obstacles acted kind of like a dam that blocked sediment traveling along the seafloor, causing it to build up thicker on the upslope side. It must have been exciting to know that there were underwater processes yet to be discovered and understood that built these submarine fans. They couldn't have foreseen that telephone lines would help them out. The fleet of ships depicted in this painting laid the first transatlantic communication cable from Newfoundland to Ireland in 1858. What an amazing accomplishment! By 1936, there were several cables going across the Atlantic as well as to the south from the hub of Newfoundland. But in that very year, a large 7.2 magnitude earthquake broke 12 of these telephone lines, creating a great disruption to communication. It was surprising to engineers that so many cables over a very large area had been broken. What a quake! It was 16 years later in 1952 when geologists revisited the data and determined that it was a huge underwater event known as a turbidite that had caused the breaks in the cables. The cables didn't break all at once, but rather sequentially. As the turbidite flowed down the slope, it encountered one cable after another, destroying them. Furthermore, they mapped the turbidite deposits and determined they extended down the slope some 600 miles into the deep water. In 1955, a paper written by Henry Menard showed a single two-dimensional echogram of two channels off the coast of Washington state in 8,500 feet of water. This information added even more intrigue to the deep oceans. On our modern map, the echogram was acquired here. It crosses the two branches of the Cascadia Channel emanating from canyons near the mouth of the mighty Columbia River. In the paper, he mentioned that there were several geologists excitedly watching the echogram in real time as it came in. They couldn't have known that this channel, named the Cascadia Channel, carried some 800 miles out into the abyssal plains. And they certainly didn't know that the channel carries sediment on three tectonic plates. It starts on the North America plate, crosses a subduction zone onto the Juan de Fuca plate, then entering a great transform fault, crosses onto the Pacific plate. Wow! They couldn't have imagined how common they were around the world, and how extensive and long they are. Even today, there are only a few limited places where the ocean floor is imaged at a high enough resolution to see these marvelous features. The great Himalayan mountain range fronting the Tibetan Plateau stretches over 1,500 miles and contains the mighty Mount Everest. Two great rivers, the Ganges and Brahmaputra, receive the vast majority of the water and sediment draining off the south side of this great range. They join to form the Ganges Delta, which is the largest in the world. One has to wonder if there is also a submarine fan with possible associated channels out in the deep ocean below the delta. What do you notice in this image to help answer that question? My attention is drawn to the canyon cut into the shelf, the steadily increasing water depth to the south, and most of all, the smooth ocean bottom. The smoothest extends way to the south, at least 2,000 miles. Could it be that sediment is being transported that far? Like the vast majority of the oceans, this region has relatively low-resolution imagery of the floor. However, scattered about, one can often find windows of high-resolution imagery. Let's look at a few of these windows, starting in the north and working to the south. The first one is here. They're a bit difficult to see. There are two segments of channels here and here. There are several others if you look carefully. Looking further to the south, we see two more segments. Even further to the south, we see three independent channels. Wow! We're getting way south now. I see evidence for two separate channels here. And now we are way south, over 2,000 miles from the shelf edge. This was the last piece of channel that I could find with the data set we have available to us. I had fun connecting various channel segments with a line to show the likely path of the current active channel. When you see the channel on the globe, it seems rather unbelievable. In fact, this is the largest sedimentary deposit in the world. So the erosion of the mighty Himalaya mountain range feeds and built the largest delta in the world and also the largest submarine fan in the world. That delta sure looks small in comparison to the fan. To my handy whiteboard here to help us understand this Bengal fan system. It's massive, and we're looking at a cross-sectional view. The tree helps us understand that. Looking sideways, this would be the ocean here, the sea bottom here. The fan, of course, has been building out sediments, the submarine fan out here onto the original ocean floor, which I have depicted here. And if you'll recall, we have the Himalaya mountains playing into this picture because it feeds all the sediment that builds out the world's largest delta, as I mentioned, and also the world's largest submarine fan. I thought it'd be fun to use Mount Everest as a way to help us communicate scale. And it does lie within the Himalaya mountains, so it plays a role in this whole system. Now, Mount Everest is 29,035 feet tall. That's 5.5 miles. We're talking a big mountain. Of course, we know it's the tallest mountain in the world. But a question for you. If I were to draw Mount Everest and have the base of it sit right on top of the seafloor with all this sediment here, and just draw it here to scale, at least the height of it, would the peaks poke above the ocean here? I'm going to draw it right here where the water's 4,000 feet deep. Would they poke above the ocean, and if so, how far? Have we got a thought? Let me sketch it for us. Okay, right here, 4,000 feet of water. Here it goes. Oh, it only comes up halfway through the sediment pile here within the Bengal fan. So that means all this sediment here, the thickness of it is some 10 miles. I hope that helps you think about it. And remember, it continues on out, gently getting a little thinner for some 2,000 miles. Now, the way this can happen is it loads the crust, the oceanic crust. There's so much weight, it starts pressing the crust down into the mantle, and it starts creating its own space as it pushes it further and further down, building more and more sediment on top.
As more and more data came in, geologists began to get indications that at least on some fans, there could be an entire network of channels like we see on deltas. This fan in particular reveals to us what many of the submarine fan surfaces would look like if we had high-resolution data available. This network of channels is certainly reminiscent of a delta. As we follow the main active channel, we can see that the channels are the backbone of the fan and distribute sediment all across the fan back and forth through time.
Unlike many of the channels or channel systems, this one is currently quite active. Out at the end of the main channel in this area here, deposition has been occurring for the last several hundred years. They have sampled this area and determined that the deposition rates are 3 feet or even a bit more per 100 years. This is very high for geologists. We've observed that often channels start in canyons cut into the shelf. It turns out that these canyons help focus the flow of any turbidites that are initiated within the canyon, resulting in a focus of energy that initiates erosion and channel formation out beyond the canyon. Of course, they also focus the muddy waters of rivers that find their way into the canyon. There is a lot we don't know about these processes, but based on modeling, it seems that once this focused flow gets out beyond the canyon, that the often subtle undulations or topography of the seafloor helps keep it focused as it continues its journey out into the abyssal plains. They kind of take on a life of their own, much like rivers that we know often do. Two parts to my sketch here. First, over here is a map view looking from above. This is a submarine fan with the network of channels on top of it. And the canyon would be up in here, of course. This is just the seafloor where I'm going to sketch this channel and describe it a bit more. The turbidite that I'm going to show you is coming out towards us. And even though there's a focused part of it, it's still quite big and broad. So let me sketch that. It's quite a big old turbidite, full of mud and the lower parts sand and silt, coming out towards us. And the amazing thing is the slope here. The slope for the vast lengths of these channels is typically like 1/3 of a degree, which means they're only flowing along at like 15 miles an hour. But they still have the ability to scour a channel. It came out of the canyon, and the middle part of it, somewhere in the middle, is going to be a little bit more focused, and it begins to scour. It begins to cut into the seafloor. Now, this is fairly easy to do because the seafloor, the deposits on the seafloor here are 50 to 80% water. It's almost like soup. So it begins to scour a channel. Let me put one right in here. I'll dig into the seafloor here and scour it out and put this channel in, like so. Now, the velocities, as you might imagine, within the channel are pretty focused. So there's going to be a lot more of the coarser material like sand and silt right in the core of the channel where the velocities are higher. But this big cloud of turbidite here, it's a big guy. It can easily be 1,000 feet tall, and it's spilling over the banks. This focused flow is here, but there's some obviously going out beyond the bank. And when it comes out over here, the velocity is slightly lower, and this focused sand and silt that's in this area starts dropping out and forming levees. So let me sketch these levees. It builds out kind of a hump that tapers off on each side of this channel, and slowly building them. Each event builds more and more of the levee. And the interesting thing is the bottom of the channel, after a deposit, it puts a little sedimentation in here too, so it builds layers in the channel as well as on the levees. So everything is building up through time. The bottom is building up, but not maybe quite so quickly, and the levees keep building up and out. This process is very much like rivers that we're familiar with. At least some types of rivers build levees, such as the Mississippi River. It builds levees, but they're about 6 feet tall, whereas these can get up to 300 feet tall or more. So, boy, they get really big out here. And just on this side of a levee, it can be 5 miles or more, one side of the levee. So these are very big features, and there's a lot of sediment associated with them. Now, as this continues to build up, I mentioned the bottom is building up as well as the levees. It gets higher and higher above the background seafloor, and that's unstable. And at some point, a flow is going to cut through a levee, and everything's going to cut off and go to a new direction. And that's why we have this whole network of channels. They jump around from side to side and sweep across that fan, building it out.
On this seismic image, we see an actual levee and channel. I've highlighted in pink the levee deposits of this channel that is aggraded or built up through time. This is on the Mississippi fan of the Gulf of Mexico. Although you can't see them, there are levees built up on every single channel you see here on the Congo fan. There are examples of channels that don't have levees, and there are examples in the rock record of channels that don't have levees. In fact, the channel that we visited doesn't have levees. Just when you think you understand how these systems work, Mother Nature throws a curveball. This channel, referred to as the Northwest Atlantic Mid-Ocean Channel, or NAMOC for short, like the Ganges Channel, is over 2,000 miles long. But unlike the Ganges, there is no great river feeding it, nor is there a canyon cut into the shelf at the head of it. How can this be? This region is far in the north. Could it be that glaciers are somehow responsible? Looking along the west coast of the Labrador Sea, one observes many small feeder canyons that go into NAMOC. This suggests that at one time there was sediment pouring into the sea all along the coast. Knowing that glaciers move tremendous amounts of sediment, one shouldn't be surprised that the great continental glaciers of the last ice age were responsible for providing huge amounts of sediment all along the coast, feeding NAMOC. Seeing this amazing channel going along the bottom of a great subduction trench along the Chilean coast makes me wonder what other great underwater rivers exist that we don't know of. And also, what other surprises await us as we continue to gather information on our mysterious ocean depths?
I hope you've enjoyed watching this video. I know I've sure enjoyed making it. I enjoy all these, actually. But I would encourage you to go to the database that has the seafloor imagery that I've used in this video and explore on your own. You're going to find channels on your own and other features that amaze you. I'll provide a link in the description to this video to that data set. And also, if you're feeling so inclined, I'd appreciate it if you subscribe to my channel. Thank you.